Hi there. Today we're going to talk about all things quadratic. Previously we did everything linear. Today we're going to look at all things quadratic. This slide kind of shows the different things that we're going to look at: graphing, looking at it numerically, being able to do algebra where you're solving equations. Let's start with graphing. A quadratic equation can be written in different ways. This particular form right here is called standard form, and it is awesome for graphing. Let's review real quick on what those variables stand for. Recall that the a value is going to do stretching and shrinking of your parabola. It also might reflect your parabola upside down if it happens to be negative. The h value moves you left and right, but because it's inside the grouping symbols, so whether they're parentheses or absolute value or a square root, anything inside the grouping symbols will always do the opposite. So if it's a plus, you actually go left. If it's a minus, you'll go right. The k value is your up and down translation, and you do whatever that sign says. If it's plus, we go up. Let's look at this example. The first thing I pick out is that translation, that left and right movement, because what it's actually moving is your vertex. Your vertex on a parent parabola would start off at the origin, but it's going to shift around. This particular one is going to go right 4 and up 3. Let's plot that. Right 4, up 3. This is going to be our vertex. The other thing that you should notice here is this a value. Because it's negative, I know that this parabola is going to open downward. And this 2 is going to actually be a stretch, a vertical stretch. On a parent graph, this a value is a 1. Anything that's bigger than 1 is going to be a stretch. Less than 1 is going to be a shrink. I think of it sort of like a rubber band. When you stretch a rubber band, it makes it and pulls it really skinny. The bigger this a value is, the skinnier your parabola is going to be. So I guess I just need to be more specific about, yeah, it's going to be skinny, and yeah, it's going to be upside down. Can I actually plot points? At this point, I'm looking to be efficient at this graphing. I want you to remember from our toolkit that we did the other day, on the parent graph, if you plug in 1, you get 1 back. If you plug in 2, you get 4 back, because all you're doing is squaring it. Remember, it's just a y equals x squared is your parent graph. So this is the table that you're supposed to know off the top of your head. What changes here is this y value that used to just equal x squared is now 2 times whatever it used to be. This a value is getting multiplied by my squared term. That's going to make my y values twice as big as they normally would be, which means all of these y values in my table are going to get multiplied by 2. And it's actually a negative 2. I'm just going to remember the negative is going to make it go downward instead of upward. I'd like for us to be able to do this times 2 and this whole table idea all in our head. I wanted to show it to you here, but ideally you're just going over to your vertex and you're saying, normally I would go over 1, up 1. That's the 1, 1. But on this example, because of the negative 2, I'm going to get over 1 and I'm going to be down 2. That's my new point right here. And put its matching point on the other side. Let's try that again. The parent graph would be 2, 4. I'm going to have to go 2, and then I'm down twice that. Over 2, down 8. So to here. Put the matching point on the other side. The parent graph would be 3, 9. I'm going to go 3, negative 18. Always taking this times negative 2. Go ahead and sketch your graph, hit all the points, nice and neat, put arrows at the end to show that it continues. That was not nice and neat, I apologize. Let's try another type. What if it's not in that nice standard form? What if it's in this form? This doesn't look like something where you see your h and k. When you see a quadratic that's in this form, we typically do factoring. Let's try to factor this, and we're going to do some factoring later on. Let me change that. I didn't leave you much room, so I'm going to have to write this up here because I know I'm going to run out of space. And we have all different kinds of ways to factor. We'll talk more about it later. I'm just going to say factors of 2x squared are 2x and 1x. Factors of 45 could be 9 and 5. That would get me an 18 and a 5x. That is not going to get me a 21. If I trade the 5 and 9, I'd have a 10 and a 9. That's not going to get me what I want. I don't think that... Oh, I goofed that up. I'm not going to be able to get rid of that 9 and 5. Sorry, this is going to get messy. What it's really going to be, I'm going to try some different factors. I think 15 and 3. I don't want to take the 15 times the 2. I'm going to put the 15 over here, and this is now going to be a 3. Then when you check your outer and inner, you got a 6x and a 15x. There's your 21x that you need. These are both going to be pluses. Typically when we factor, we set it equal to 0, and we will set each of those quantities equal to 0. I would end up with an x equals, for this first one, if I set it equal to 0, I'd end up with a negative 15 halves. For the second one, if I set it equal to 0, I'd end up with a negative 3. I've solved this problem for x. However, why did we magically turn this y into a 0? What are we doing there? Well, if you think on a graph, where does y equal 0? Well, y is 0 anywhere along here on the x-axis. If I make y be 0, when I go solve this, what I have found are the two places on this axis where my parabola will touch. These are actually your x-intercepts. That's what we just found, the x-intercepts. Let's plot them. Negative 3 and negative 7.5. The other thing that you need to find, I know where this is going to hit my axis, and because my a value, even in this form, this a does the same thing. This a value is going to make it open upward, and it's going to make it be a little bit skinny. But I don't know how far down to put my vertex. Like, is it here, or is it here, or is it way down here, or where would I put it? This little formula, if you'll recall from Algebra 2, helps you find your vertex. The x value of the vertex will always be the opposite of b over 2a when your quadratic is in this form. In this example, the opposite of b would be negative 21 over 2 times a. A is 2, so it's going to be over 4. That's not very pretty. Probably in Algebra 2 it always came out nice for you. It's not going to for us. The vertex is approximately negative, well, it's right at negative 5 1/4. I know that's how far over it's going to go. Negative 5 1/4, which should kind of make sense. That hits smack dab in the middle of your two x-intercepts. The second part is a little trickier. You have to plug in to your equation that x value. If I plug in negative 21/4 back in for all the x's, could we solve this for y? So I'm going to go to my calculator, and I'm just going to type in 2 times negative 21/4. And really, if you wanted to call that negative 5.25, that would work too. Squared plus 21 times your negative 21/4. Oops, forgot my negative. Bear with me. And then add your 45. I end up with a negative 10.125. That's the y value of your vertex. If I want to plot that on my graph, I'm over left -5 1/4, down 10 and a little bit. And with those 3 points, we should be able to get a reasonable looking parabola here. There you go. Let's talk about a few things that might happen. What if it doesn't factor? Up here, this happened to factor beautifully for you. If it doesn't factor, well, you're going to do quadratic formula. And it's just not going to come out nice, and that's okay. You can, okay, so that's this part right here. You could still find your x-intercepts by doing quadratic formula. You could still get the shape of it if you remember that this a value still does the same thing. That 2, really from right here, I could go over 1 up, not up 1. The parent graph is up 1. I'd go over 1 up 2. I'd go over 2 up 4. I'd go over 3 up, oh, I'm sorry, not over 2 up 4. Over 2 up 4 would be the parent graph. I'm going to go over 2 up 8, and then I'm getting pretty close to the top there. All right, let's move on. What about writing the equation? I already have some details about the function. Could you write the equation? Hopefully yes, but let's go through it. Let's get a little sketch so we see what's going on here. I have a vertex at -2, -5. So somewhere like right here is my vertex. That's not very good. Let's try again. -2, -5. Down here a little bit farther. I know that it's going to pass through the point -4, -27. Holy cow, that's down here someplace. So I know the parabola looks something like this. I'm supposed to write the equation of it. By them telling me the vertex, I really know the whole shifting. I know that it went left 2 and that it went down 5. That's really your h and your k out of your equation. The other thing that you know is this ordered pair that's supposed to work in the equation, so this would be your x and this would be your y. If you look at your equation, you've got h, k, x, y, you've got everything except for a. Let's go figure out the a value. Let's see how skinny this parabola is. Just plug in all the numbers. -27 equals a. Your x value is -4 minus your h value is -2. Don't forget that squared, and then -5. This ends up being a -2 squared, so that becomes times 4 minus 5. Do not try to subtract this. Order of operations says you got to do this first, and we can't really do anything with it, so I'm bringing the 5 over. Add the 5, divide by 4. This is not a very pretty a value, but that's okay. We're going to live with it. That's what it is. Now you know the a value and you know the vertex, you should be able to write your equation. Go back and put your x and y back in it. So it's going to be y equals -11/2, and in parentheses it's going to be an x. Since it went left 2, it's going to end up being a +2. Don't forget your squared. And then it went down 5. There's your equation. That's looking at quadratics numerically. If I give you all the numbers for it, can you turn it into an equation? Let's start talking some algebra. We're going to do some factoring, some solving. Like I said earlier, there's so many different ways to factor. I'm going to show you how I do it. I know you might do the Boston method or the AC method, or you might do a grouping method. Lots of ways. I just do this kind of mentally. We're to that point where we try to do quite a bit of math mentally. Let's see how we do. Factors of x squared are x and x. Factors of 10, I could do 2 and 5, or I could do 1 and 10. Because of the minus sign, I know I'm going to have one of them positive, one of them negative. This is beautiful for a -5 and a +2. That would get us an outer of a 2x. Inner is -5x. That gets us what we need. I should have suggested here when what we did in class is go ahead and pause the video. Do as many of these as you can. You might save time rather than having to listen to me and write it down and all that business. Just do what you can. Come back and listen to the ones that you need to that you need help on. All right, so let's finish this one up. Factors of 36, I could go 6 and 6 or 12 and 3. Looking at what I'm shooting for, I know that the signs are the same, and I want to end up with a negative 15. I can make that happen with a minus 12 and a minus 3. Let's make it a little trickier. This problem has a 5 for initial term, so it's going to be a 5x and a 1x. And then I can pick factors of 6, but I know my signs are going to have to be different. And then I'm going to try to combine it and get back to a 29. So I'm needing a pretty big number so that it will reduce back to a 29. If I'm going to choose, I guess for 6, I'm going to go with 6 and 1. Let's look at what happens. You choose 6 and 1, that gets you clear up to a 30x and a 1x. If I subtract those two, I'll get my 29 that I want. I want it to be a negative 29, so we're going to have to make that negative 30 and a positive 1. Next problem. 6x squared, I could go 6 and 1 or 2 and 3. I'm going to try 2x and 3x. I know that it's going to have to be a 5 and 1, and I know that I'm going to want to subtract them to get to 7. I think if I put my 5 here, that would get you a 10, and put a 1 here to get a 3. 10 and 3 have that difference of 7. I want it to be a negative 10 and a positive 3. Next, getting trickier. This one I threw in here just so that you understand that sometimes that Boston method or that AC method where you're multiplying the first times the last, this is going to get crazy if you try it here. But if you just try to come up with factors, I mean factors are 22, I'm pretty sure it's going to probably be 2 and 11. I know one's going to be positive, one's going to be negative. So I'm going to look for a difference of 43. I need something to end up getting bigger than 43. What if I put in a 5 and a 6? So what if you did 5 and 6? Of course, those would have x's on them. Let's check and see if that works. It may not work. I have a 12x and I have a 55x. If I do a 12x and a 55x, and since I want it to be a negative 43 in the middle, I'm going to make my 55 negative. I don't know, what is negative 55 and 12? Hey, what do you know? That's negative 43. Didn't we get lucky there? I almost put my 6 here and my 5 here. I don't know why I just dropped in that 5. Sometimes you'll try something and then it doesn't work, so you have to swap them and try a different one and see. Just trying to make the outer and inner get you this middle number. Put in your minus for your 55 and your positive for your 12, and you've got the factors. Last one, this one is a difference of squares. These are the ones where you just square root each term. It's a 2x and a 9. One of them's a plus, and then you go do the opposite, 2x minus 9. Difference of squares. You have several of these to practice factoring. I don't care what method you use, as long as you know how to factor. The last thing here we need to look at is a bunch of solving. And what we did in class is I just turned you loose. Go solve as many of these as you can. And you're really probably going to save time if you just go do as many as you can by yourself and then come back and watch the ones that you need to watch. So pause the video, go do the next 4 slides, and then come back. This first example. In general, we're going to be doing some factoring. That's why we practice that first. Different ways to factor. On this one, there's only 2 terms. The very first method that you should always try is pulling out a GCF. In this case, I could pull out a 3x, and then I'd have a 2x minus 1 left. These are a little bit different than the previous where we were just factoring. Now they equal something. You always want your quadratic to equal 0. If it equals 0, then you know this is 0 or this is 0, which makes your next step just setting each of those equal to 0. We kind of did this on that quadratic earlier. X is equal to 0 or 1/2. There's your solution. On the second problem, it looks like something a little bit normal, like you got this trinomial that you're going to factor, but notice that it does not equal 0. It only works if you make it equal 0. So let's bring the 3 over. And then once it equals 0, that's when you get to start factoring. So 2x and x need to get up to a 9, so it's probably a 4 and a 1, 8, and yep, that works. Then you're setting these each equal to 0. How much of this work here you show is kind of up to you on how well you can do the mental math. I'm going to subtract the 1 and divide by the 2. I'm going to subtract the 4. This third example looks like they already factored it for you, but unfortunately they factored it before it equaled 0. So that is not helpful to you. You actually will have to FOIL this back out. So I'm going to have a plus 2x and a minus 5x, so minus 3x. FOIL it out, and then it's like the previous one, you got to make it equal 0. Set up your factors, x and x, factors of 18. Going to have a difference of 3. It's going to be a 6 and a 3, minus 6 and a plus 3. When you set them each equal to 0, you should have a negative 3 and a positive 6. Example 4, again, it doesn't equal 0 like we need it to. Every time you have this power here, you want this to equal 0. The best way to make it equal 0 is to bring everything to the same side. I end up with 3x squared minus 5x equals 0. Looks like problem 1. Let's pull out a GCF. Looks like only an x can come out of that, but that's all right. That gets your number or your variable, your powers a little bit lower. Look at this. If you set those each equal to 0, you'll get x equal to 0. And on the second, on this quantity, you'll end up with an x equals, I would add the 5, divide by the 3. I'm moving pretty fast here. I guess I'm thinking that most of this should be review. So if you need to rewatch it because I flew through it too fast, don't be afraid to do that. Do what you need to do so that you'll understand. I'm going to do a couple things on this one. I'm gonna do it wrong first, so don't write this down. Typically, what people want to do on this first example is go ahead and, like on the previous, go ahead and FOIL it out, and then bring the 16 over, and then refactor it down. It can work. That's a whole lot of work. I want to show you a couple things here, though, that are important. First of all, if you decide you're going to square this out, do not take this 2 and distribute it. This power does not distribute in parentheses. What you would have to do is write out x plus 3, x plus 3, and FOIL it together. You should end up with a middle term. But let's talk about something. We're kind of at the stage where we should start to notice some patterns. When you multiply this out, your first will get you an x squared. Your outer is a 3x, but you're also going to have an inner of 3x. This will always happen if the two are the same. Your outer and inner are the same thing. And then you get a plus 9, which gets us to x squared plus 6x plus 9. What I'd like you to be able to do, though, is to get from here to here without showing all this work. Let's look at where it came from. The first term is just this term squared. The last term is just this term squared. And look at where your 6x came from. It's from the 3x twice. If you just multiply these two together, there's your 3x, and then double it gets you your 6x. Let's practice a couple. Well, let me see if... Okay, I'm going to end up scribbling that out, but I want to practice just a couple. What if it was x plus 9 squared? Could you do that without all the FOIL? Well, idea squared, 2. Your middle term, multiply the 2, that's 9x, then double it, because there's going to be 2 of those. All right, we can even do it fancier. It's going to get really cluttered, sorry. Let's go 2 square that. This next problem is kind of similar to a previous one. You're going to want to set this equal to 0. Go ahead and subtract and get everything on the same side. Make it equal 0. Got that. Pull out your GCF. I could pull out a 3x squared on this one. And then I'm going to have x squared minus 16. And what you actually end up with there is a difference of squares that could factor again. Setting each of those equal to 0 on this first term, if I set this equal to 0, x is just going to be 0. The next one, x is going to be negative 4. This will be x is positive 4. There's your solution for that one. Last one. This is the trickiest one, the one that people mess up the most. It's very, very tempting on this problem to get rid of the square root by squaring everything. And kind of, yeah, that's what you're going to do, but you don't get to just square, square, square. It doesn't work like that. What you're doing is you're squaring both sides of the equation. And before you do that, you're going to want to make sure that this radical here is isolated. I need to move this plus, or this x to the other side. We're going to rearrange this and get that radical isolated. Now we're going to square both sides. Square this. That's going to work beautifully over here. Oh, look at what we've got. We're going to do that squaring thing. On the left, the square and the square root cancel, and you just have 3x plus 10. On the right, let's do our shortcut. X squared for your first term, multiply the 2, which is 4x, double it, gets you an 8x. Square the last term. Again, you can't take this square and just distribute it in there. We end up with this quadratic. I'm going to want this to equal 0. Let's bring everything over. I'm left with an x squared, subtract the 3x, subtract the 10. Now it's going to equal 0. That's actually going to factor beautifully for us. Factors a 6. You're going to get us a 5. It's going to be a 2 and a 3. They're both pluses. X ends up equaling negative 3 and negative 2. One thing you do need to watch out for on certain types of equations is checking to make sure that your answers really work in that problem. When I see this big square root, I'm always nervous, oh wait, that might end up negative under there, especially since I'm getting negative answers. Let's throw those numbers in and see if they work in this problem. If you take a negative 3 right here, you're going to end up with negative 9 plus 10. Well, that's a positive 1, so that's good. I'd have a 1 minus, and then for the x, I plugged in the negative 3. Sorry. Okay. Negative 3, that's a plus plus. All right, 1 plus 3, yep, that's 4. Looks good. Let's try the negative 2. If you put negative 2 in, you're going to end up with a negative 6 plus 10. That's 4, but the square root of 4 is really just 2. That's going to work out okay then, but does it finish out? So it would be a minus negative 2, which turns to plus plus. That gets me my 4. It all checks. We're good to go. But something to think about that you got to be careful sometimes. All right, that's a lot of solving. I tried to give you a lot of different types of problems so that you're kind of back in the groove of being able to solve about anything I give you. Let's try a couple applications. Now that we know how to do all that solving, let's go ahead and use that on some applications. Let's start with this first one. It refers back to yesterday's problem on that serial. Recall that we had this big table given about the price that we were going to charge for cereal and then how much we could sell, how many boxes of cereal we would sell based on that price. That was yesterday. And we kind of learned that as you increase the price, you're not going to sell as many. It wasn't rocket science, but it did have a linear relationship, as specifically as you kept raising the price, what happened to your sales. If the demand for some product is linear, the revenue, that's the money that you make, not the profit, but just money that comes into your account. The money you make is going to end up being quadratic. Well, since we're talking quadratics today, let's talk revenue. You have to think about how you make money. How do you bring that money in? Well, you look at what you charge for something, the price of it, and you take it times however many of them you sell, and that's your demand function. We can write then our revenue function, R of P, revenue with respect to price, is going to equal the price times our demand function. We have to look back yesterday. Yesterday, you should have in your notes that the linear relationship from this table that we had, we ran a regression on our calculator, it was negative 15,350. I'm going to round this just to a whole number, times X, or P for price, plus 73,623. If you look at this and go ahead and distribute that, it might make more sense. You don't have to do this, but do you see if you distribute the P, you have a negative 15,359 P squared plus 73,623 P. Either way, it's a quadratic. This way, though, then you can kind of see, oh, it's going to be a negative, it's going to be an upside down quadratic, upside down parabola. Let's talk about what's going on. If you make P equal 0, if you charge $0, you're going to make 0 money. 0 should be one of your first points there. But it's an upside down parabola, so it's going to look something like this. What's happening is as you increase the price, you start making more money. But there's kind of this tipping point at which you start charging so much for it that you just can't sell enough boxes anymore, and your revenue starts to decrease. Well, in a perfect world, this right here happens. And actually, a lot of companies, they have analysts that determine this for them. What's my best bet? They do this market analysis, and they figure out what's your best bet to make the most money. If you go off to college and you're going to be a math major, that's the kind of thing that you end up doing. You end up being an analyst for a company somewhere doing this kind of work for them. We need to find this spot right here. There's two ways that we can do this. Earlier we learned that we can do that algebraically. I can find, that's just my vertex. I can do the negative b over 2a thing and go find the vertex. That's one option. Got some big numbers here. It might be kind of messy. I'm going to look at option 2, which would be to go to your calculator and find it. Let's review how to do that from previous classes. Your calculator can find this maximum. What you need to do is type in this equation, or this one, doesn't really matter, into your y equals. If you go into y equals, type that in, and your bigger issue on this is going to be finding a window that matches it. If I type in, I guess I'm thinking my p is my x, and I can look at my little picture here and say I don't really need to go negative. I'm going to go 0 to, well, remember from yesterday, what kind of prices did we have? There were like $2 and $3 and $4 and $5, and so I'm going to go with, let's go 0 to 10. For my y's, that's how much revenue I make, so I'm going to start at 0, and then I'm going to put for a y max. If you look at your equation, you got some big numbers going here. I'm going to throw in a 100,000. And then scale it by 10,000. and then graph it. And you should get a beautiful graph that shows this maximum. All right, to find that maximum in your calculator, you go to second trace, and the maximum is number 4. You just hit the 4, and then you have to find your left bound, so you scoot your cursor a little bit left of the maximum, and then you scoot your cursor a little bit right of the maximum, and I just press enter, and boom, it gives you the maximum right here. Well, that would round to 2.4, comma, the y is 88,220, it would round to an 8. I'm going to round that off. And that's your answer. Boom, done. But my bigger question is, do you know what you just figured out? Do you know what this means? Officially, you should always be writing me a sentence that explains what just happened there. What is this 2.4? Well, that's your X, or your P, so that's the price. That's what we need to charge for the cereal, $2.40. This is your Y, or your R, that's your revenue. Okay, a nice sentence would be something like, you can maximize your maximize your revenue at $88,228 if you would charge $2.40 for each cereal box. Give me a good sentence that explains that you know what just happened or what you just found there. All right, one more. Let's look at one more problem. This is another application, a pretty common type of quadratic application. It's called vertical free fall motion. It's like when you throw a ball up in the air and then it comes back down, and it's kind of forming this upside down parabola. This is your formula for vertical free fall motion. You don't really have to memorize it, but you have to understand it enough to use it. S of t, so S usually stands for position, so the position of the object with respect to time is equal to -1/2 g. G is the acceleration due to gravity. On Earth, we call it 32 feet per square second. Times your time squared plus the initial velocities. You'll need to be given how hard are you throwing that ball up in the air. Times your time plus S sub O is your initial height or your initial position. Anytime you have a sub-zero, that's always your initial value. That also is going to be given to you. Let's look at an example. We have this pitching machine. It's rotated to throw pop-ups. It's going to throw with an initial velocity, so we're going to know that, and an initial height. We know that. They want us to write the model. I'm just going to fill in values. All you got to do is write the model. S of t is equal to -1/2 times g. Going to do some mental math. G is just 32. Ends up being a -16 t squared plus the initial velocity. They told us was 48. 48 times t plus initial height, they told us was 3.5. That's all you're doing there. You're just writing the model, filling in the values that they give you. But then part B, we want to use that model for something. Hopefully you look at this and you recognize it as an upside down quadratic. Should look something like that. Throwing the ball up, coming back down. They're asking us for the maximum height again and the time that it takes to reach that height. I'm looking for this spot right here. Just like last time, you could do this algebraically or you could do it graphically. You can type this into your y equals and go find the max, or you can do the -b/2a. Sometimes I find that using my calculator to do it graphically takes more time because I'm having to mess with my window a bunch. I'm going to try this one algebraically. It's actually going to work out real nice. The vertex is -b over 2a. 48 over 32 actually reduces. 16 goes into both of those. That vertex ends up being just a 3/2, or 1.5. That's pretty easy to work with. I'm going to stick with this algebraic method. I'm going to take my 1.5 and plug it in to my calculator for the t value. I'm plugging it into the equation, but I'm going to my calculator to do that. I'm going to have negative 16 times 1.5 squared. It's 48 times 1.5 plus 3.5. I end up with a value of 39.5 for that vertex. But I always want a nice sentence that explains what on earth did that we just find there. Recall that this is your x value, or for this problem, the t value, which is time. At 1.5, this is measured in seconds, at 1.5 seconds, the y value is like your s, or your position. That's where the ball is, how high the ball is. A nice sentence might be, the max height is 39.5 feet after 1.5 seconds. Write a nice sentence for me. All right, I know it's gotten long. Thanks for hanging with me. Good luck.